Welcome to EDU World Space.
Okay, so we're doing chapter 32, problem 22. So they want us to use ray diagrams to show that the mirror equation is valid for a convex mirror, but as long as we take the focal length to be considered negative. So we want to show this geometrically and derive this mirror equation. So let's start out by drawing our ray diagram here. So this will be our plane, and then we'll make the mirror here. Let's call this our focal length, and let's extend it out a bit, and this can be our radius of curvature. Cool. So let's put an object here, and this is at a distance d naught. We consider our object distance. So let's figure out where the image will be formed by doing our ray tracing rules. So first one will be coming in parallel, and it'll bounce back like it came through the focal length, like that. Cool. The next one is going to go straight through like it was hitting the radius of curvature. So it's all the way like that, and it'll bounce straight backwards. The next one is going to bounce in right on the axis and bounce back like a plane mirror. So if we trace these back, we should see that we're left with a little image right here. So now we want to figure out if we can derive what this image distance is. So let's draw some angles here. First, we know this is theta and this is theta because this is just a plane mirror interaction, which is angle of reflection equals angle of incidence. The other angle we can describe here is this is also theta. We can also say this angle as alpha. So from that, we call this the object height, h naught, and hi will be the image height. So we can now use our angles and some trigonometry to define some factors. So looking at this small triangle here, we can say the tangent of theta is the opposite over the adjacent. So the opposite is hi, and the bottom is negative di, because we know the image distance is negative, it's on the other side of the mirror. This is also equal to, if we look at this triangle, using this, the tangent of theta is also equal to the object height over the object distance. So that's one of our equations we'll need. The next one, we can look at this triangle with our angle alpha. And we know that the tangent of alpha is the opposite over the adjacent again, which will be h naught, or hi, the image height. And this is a distance away from the radius of curvature. And since our image distance is negative, this total distance we can just add on the image distance to get the length here. We can also think of this as the very big triangle all the way to the object, and this will give us the object distance over the object distance plus the radius of curvature. Cool. So now using these, we can start to solve some stuff. So if we divide these two equations, we should see we have h naught over d naught times d naught plus r over h naught. We'll see these cancel out. We're left with d naught plus r over d naught. And this is equal to the other side, which will have just an I over negative di times r plus di over hi. These will cancel out, and we'll be left with negative r plus di over di. Cool. So now we can simplify this. We simplify this, we'll see we have 1 plus r over d naught. And this is equal to negative 1 minus r over di. We can further simplify this to being r plus r. This one's over d naught over di, and this equals negative 2. Cool. So let's make this even more closer to what equation we're trying to solve here. And we should see that this is equal to 1 over d naught plus 1 over di equals negative 2 over r. Cool. So now we know that f is r over 2, but we need this to be negative for our convex mirror. Because if we set this to be negative r over 2, we're left with 1 over f. And that is exactly the equation we want. So this equation works for this mirror, but only if we take the focal length to be negative. Awesome.